This is a video from section 16.3 found in a Calculus 3 class. Find a function little f such that capital F is the gradient of some little f. Use part A to evaluate the integral over c of f dot dr. 17. Suppose capital F of xy is the vector comprised of the components 2x and 4y. C is the arc of the parabola from the ordered pair 4, -2 to the ordered pair 1, 1. First, we want to show capital F is conservative. We're going to let P of xy equal 2x, and if you notice, that's the first component. I'm going to take the partial of P with respect to y and get 0. Why? Because x is constant. If I let Q of xy equal 4y, that's the second component, and I take the partial of q with respect to x, that's also 0. And if you notice, the partial of p with respect to y is the same as the partial of q with respect to x, and that says f is conservative. So it's good practice to show f is conservative. To find the potential function, in step 1, we're going to set the partial of little f with respect to x equal to 2x, and that's the first component. Okay? Then we're going to integrate both sides with respect to x. And so little f of xy is the same as x squared plus h of y. Now, why do I use h of y? The reason why is because y is constant. So that's one thing you want to really keep track of. What are your constants? Y is constant, which means y squared is constant, y cubed is constant, sine of y is constant, tangent of y is constant. They're all constants, okay? And so to capture all the constants, we would add h of y. Now we got to get a handle on h of y. And to do that, we're going to take the partial of f with respect to y. Well, that's going to be equal to h prime of y, because when you're taking the derivative with respect to y, x is constant. And so I'm going to set h prime of y equal to 4y. That's the second component. I'm using the second component to get a handle on h of y. So h prime of y is equal to 4y. And so h of y is equal to 2y squared plus k. So you find h of y the typical way you did in Math 400. So now that we know h of y, I could put everything together. F of xy is equal to x squared plus 2y squared plus k. Now here's the beautiful thing about doing that. That's my potential function. So if I want the integral over c of f dot dr, that's the integral over c of the gradient of f dot dr, and it's basically the fundamental theorem. So I'm going to take f of 1, 1, and I'm going to subtract f of 4, -2, because you're going from 4, -2 to 1, 1. So I take f of the terminal point and subtract f of the initial point. And so if you notice, x is 1, y is 1. Right? So I'm replacing x with 1, y with 1 into the function f. And I'm going to do the same thing. So I'm going to replace, for f of 4, -2, replace x with 4 and y with -2. And I did my calculation and got -21. If we take a look at 19, we get capital F of xy is equal to x squared y cubed, so it's a vector made up of the components x squared y cubed and x cubed y squared. And my curve is r of t equals the vector function t cubed minus 2t and t cubed plus 2t, where t is between 0 and 1. So once again, I'm going to show f as conservative. So if I let p of xy equal the first component, which is x squared y cubed, and I'm going to let q of xy equal the second component, which is x cubed y squared. The partial of p with respect to y is 3x squared y squared. Remember, x is constant. The partial of q with respect to x is 3x squared y squared. In this case, y is constant. since the partial of p with respect to y is the same as the partial of q with respect to x, f is conservative. To find my potential function, again, one thing I want to make sure you guys are aware of, what this is telling me is that capital F is can be written this way, basically. It's a vector comprised of the partial of f with respect to x and the partial of f with respect to y. Okay, so I'm going to take the partial of f with respect to x, and I'm going to set it equal to the first component. And a common question that I would get asked is, could I take the partial of f with respect to y and set it equal to the second component? And the answer is yes, you can, and you could work backwards, but for purposes of a video like this, I want to be as consistent as humanly possible. And that's why I look at the partial of f with respect to x and set it equal to the first component, and I work my way across. So that's what I did here. I set the partial of f with respect to x equal to the first component. Y is constant, and so I'm going to integrate both sides essentially with respect to x and get f of xy is x cubed y cubed over 3 plus g of y. Okay, that's going to encapture all the constants. Now, I'm going to differentiate both sides with respect to y, and that's a partial because it's a function of two variables. And so when I do that, I get x cubed y squared plus g prime of y equal the partial of f with respect to y. So I'm going to set this expression equal to x cubed y squared because that's the second component. So that says g prime of y equals 0 because these terms cancel. And that says g of y equals k. And that says f of xy is equal to x cubed y cubed over 3 plus k. Now, I want to find the integral over c of f dot dr. Now, r of 0, here, let's go back. So r of t, let's remind ourselves, is t cubed minus 2t and t cubed plus 2t. Right? And so when I plug in t equals 0, I get the vector 0, 0. And when I plug in t equal 1, I get the vector negative 1, 3. Well, I'm in business because the integral over c of f dot dr is the integral over c of the gradient of f dot dr, and that's f of negative 1, 3 minus f of 0, 0. And when I make that calculation, remember I'm plugging x and y into this function here. The k's are going to go away, and what you're left with is negative 9. You're done. Do you need the k? The answer is no. It's kind of like when you're doing the fundamental theorem of calculus in Calc 1. You do not need to do it when you're doing definite integrals. You don't need to have the k when you're doing the fundamental theorem of line integrals. On 21, suppose capital F of xyz is equal to the vector comprised of the components 2xy, x squared plus 2yz, and y squared, okay? We have to assume f is conservative. You're going to learn in a couple sections how to prove f is conservative. Right now, we have to make that assumption. Now, C is the line segment from the ordered triple 2, negative 3, 1 to negative 5, 1, 2. Now, to find my potential function, I'm going to set the partial of f with respect to x equal to 2xy. It's very systematic, you guys. Now, here, y and z this time are constants. So we got to be aware of that. Y and z are constants. So f of xyz is x squared y plus h of yz. Now, you might ask, why h of yz? Why not h of y plus h of g of z, let's say? The reason why is that doesn't capture like products. So if you added two functions where one of them was y and the other one was z as my inputs, the problem would be you wouldn't capture functions like this. And we need to be able to capture all of it. And that's why it's a function of two variables. And now, we need to get a handle on this function, and we're going to use the second component to do that. What does that mean? We need to take the partial of f with respect to y. And because you have a function of two variables, we're going to essentially, let's go back. The derivative of y is 1, right, with respect to y. So you're going to get x squared plus the partial of h with respect to y, right, or h sub y of yz. So you're taking the partial derivative of that function with respect to y. So I'm going to set x squared plus h sub y of yz equal to x squared plus 2yz. That says h sub y of yz is 2yz. Now this time z is constant, so if I want h of yz, I get y squared z plus g of z. Now that says f of xyz is equal to x squared y plus y squared z plus g of z. Well, I need to get a handle on g of z, and what I'm going to do is I'm going to use the third component to accomplish that goal. So I take the partial of f with respect to z, okay? And when I do that, x and y are constant, so we can't lose sight of that. So I get y squared plus g prime of z. So I'm going to set y squared plus g prime of z equal to y squared. So g prime of z is 0 because the y squareds cancel. So g of z is k. And so f of xyz is x squared y plus y squared z plus k. So the integral over c of f dot dr is the integral over c of the gradient of f dot dr. Same game. And what's beautiful about this, it doesn't matter what that curve is. I need to know what the initial point is and the end point, and the function, of course. So this is f of negative 5, 1, 2 minus f of 2, negative 3, 1. So I make my calculation, and I come up with 30. That's problem 21. Problem 23. So I get f of xyz is equal to yz e to the xz for the first component, e to the xz for the second, and xy e to the xz for the third. R of t is t squared plus 1. This is a vector value function. So the first component is t squared plus 1. Second component is t squared minus 1. Third component is t squared minus 2t. T is between 0 and 2. And we need to assume f is conservative. To find my potential function f, we're going to set the partial of f with respect to x equal to the first component, which is yz e to the xz. Now, y and z are constant. So f of xyz, remember that y and z are constant. So think of the z like 5. And don't forget, I'll give you an example. The integral of e to the 5x dx is equal to 1/5 e to the 5x plus some c, right? So when I integrate this, I'm going to take this expression and divide by z. And when I do that, the z's cancel, and what I'm left with is f of xyz is y e to the xz plus g of yz. Now, I need to get a handle on g of yz. So I need to take the partial of f with respect to y. And that's what I did over here. When I do, I get e to the xz plus g sub y of yz. Set e to the xz plus g sub y of yz equal to e to the xz. So g sub y of yz equals 0. And remember here, z is constant, which tells me g of yz is equal to h of z. Well, that says f of x, y, z is, we can't forget, we have y e to the xz plus h of z. But I got to get a handle on that h of z. So I'm going to take the partial of f with respect to z. And I get x, y, e to the xz plus h prime of z. And so that says h prime of z is 0. I'm using the third component to accomplish that goal. H of z is k. And so f of x, y, z is y e to the xz plus k. Okay, now let's take a look at something. Now we need to remind ourselves, r of t is the following. T squared plus 1, t squared minus 1, and, let's go back, t squared minus 2t. And remember, t is less than or equal to 2 and greater than or equal to 0. So r of 0 is 1, negative 1, 0. R of 2 is 5, 3, and then 2 squared is 4, 2 times 2 is 4, so it looks like we're going to come up with 0, right? Now, the integral over c of f dot dr is the integral over c of the gradient of f dot dr. But that's f of 530 minus f of 1, negative 1, 0, like so. Now, let's remind ourselves, f of x, y, z equals y e to the xz plus k. So we're in business. Now remember, let's again remind, we have x is 5, y is 3, z is 0 for the f of 530. And then for the second term, we have x for 1, y is negative 1, and z is 0. So plug in. I get 3e to the 5 times 0 plus k minus, I'm going to get negative 1e to the 1 times 0 plus k. So this is 3 plus k, e to the 0 is 1, minus negative 1 plus k. The correct answer here is 4, because those k's are going to cancel out. And that is going to do it for this video for section 16.3. We worked on problems 17, 19, 21, and 23. Thank you. And this is for a Calculus 3 class. The problems can be found in Stewart 9th edition. Thanks.